I wrote down here, recall, energy was defined as the ability to do, who remembers the punchline? Work. Now, we originally said that work was force times distance. That only works for a constant force, and if the force and the distance are in the same direction. It's actually not that useful in an equation, especially in physics 12. We also said that work was equal to, if you had a force versus distance graph, it was equal to that area. You can do a little quick sketch, or you can write out the area underneath a force versus distance graph, whichever you feel is less writing. For me, it's less work just to sketch the graph and color in the area. Today, we're going to look at the work-energy theorem. This is the best definition of work, but Logan, no pun intended, it's also usually the most work, most writing. But what's nice about it, Riley, is it's an equation, it's a concept that relates work and energy. It's why it's called the work-energy theorem. It says this: yes, I know work equals force times distance. Yes, I know work is the area underneath the force versus distance graph, but work equals delta PE plus delta KE. Triangle PE plus triangle KE. What does that mean? The triangle, the delta. And so that's going to be final minus initial. You want to know how much work you've done on an object, Jagger? Look at how much its potential energy has changed by. Look at how much its kinetic energy has changed by. That energy had to come from somewhere. Yeah, the outside source doing work. That's how much energy. That's how much work. We use this one an awful lot in physics 12. This is the one we use, for example, when we look at rocket science. If you're trying to figure out how much work, how much energy, how much rocket fuel to put something in orbit, the problem is, as you go further and further from Earth, what happens to the force of gravity as you go further and further from the Earth? It gets weaker. It's a changing force, so I can't use that bad boy. You could do the area underneath the graph, but the graph is a curve, and none of you know how to find the area underneath a curve. Calculus. So we use this one as our workaround. Workaround, nothing? Okay. A cyclist weighs 65 kilograms. His bike weighs 7.2. So you know what? Let's write down the total mass. It's going to be 65 plus 7.2. Double check me. Is it 72.2 kilograms? That's what we're going to use, I think. Yes? And usually there's always a pedantic physics nerd who points out, Ben, that I shouldn't have said a cyclist weighs kilograms, because what's weight measured in technically? Newtons. And so I've phrased this badly on purpose just to jog our memory and say a non-physics person would have no problem with that sentence, but a physics person should say, technically you mean a cyclist has a mass of 65 kilograms or weighs, and give me an answer in newtons. Anyways, the total mass is that. How much work does it take for him to increase his speed from rest to 5 meters per second? Adam, what's this question asking us to find? How much what? How much what? One word. How much what? How much what? So don't write this down. My first thought would be, well, don't write this down. Did they give me a force or a distance in this question, Adam? Do you see newtons anywhere? Do you see meters anywhere? So I would, in my mind, scratch that one out. My next thought would be, well, it's the area underneath the graph. This one's meant to be Captain Obvious. Did they give me a force versus distance graph? Ain't that. So as a last resort, but an all too common last resort, I go to the work-energy theorem. So can all of you write down work equals the change in potential plus the change in kinetic. By the way, you should also have found where that is on your green sheet. I think it's just below the conservation of energy equation, yes? Now, this change in potential, that only occurs when you have a change in height. I don't see this question mentioning a change in height at all. So I'm going to assume we're on level ground. I'm going to assume that if they wanted me to have a hill, now if they gave me a hill height, that would be my change in potential. But I'm going to assume level ground. So I'm going to assume that I can cross that out because I don't see a change in height anywhere. Okay with that, Courtney? Okay. Courtney, what's changing anything? So the change in kinetic energy, the work, is going to be KE final minus KE initial. It's going to be a half mv final squared minus a half m v initial squared. Although, Sam, I can see you glaring at me. You're right. It does say from rest. I could have crossed out the initial either on that line or on the previous line. How much work, how much energy will this cyclist have to give from his or her body to go from 0 to 5 meters per second? It's going to be 0.5 times 72.2 times 5 squared, which is what? You get 902.5 joules. B. What if he wants to increase his speed from 5 meters per second to 10 meters per second? So we would start out with the same argument, Evan. I would say, well, it wants me to find how much work. And so my first thought would be, don't write this down, to go force times distance. I would say they didn't give me a force. They didn't give me a distance. I would say to myself, it's also the area underneath the force versus distance graph. I don't see a graph. So my last resort, my third definition of work, but the most common one, to be honest, it's going to be the change in potential plus the change in kinetic. And again, Evan, I think I can cross out the delta PE because I don't see a change in height here anywhere. Good, Jan Jackson? Good. Evan, what's changing anything? So this is going to end up being a half mv final squared minus a half mv initial squared. What's kind of neat about this, Blake, and I've mentioned this earlier, but I'll repeat myself, this squared affects your life in ways you don't realize. By how much, Blake, is he increasing his speed? Do the math in your head. In A, how much was he increasing his speed by? Also, but you're not going to get the same answer. And the reason you're not going to get the same answer is that squared means the faster you go, the more work, the more energy it takes to go a little bit faster. It's going to be 0.5 times 72.2 times 10 squared minus 0.5 times 72.2 times 5 squared. What do you get? You get 2707.5? Yeah. Joules. What if I wanted to go from 10 to 15? Let's see if we can jump straight down to plugging in the numbers. We would do the same argument, Courtney. We would say, well, work equals force times distance. You would say, I don't see a force. I don't see a distance. I would say, work is also the area underneath the force versus distance graph. You would say, graph. And I would say, oh, work is the change in potential plus the change in kinetic. You would say, I don't see a change in potential or height here anywhere. You know what? I think it's going to be, the work is going to be a half mv final squared minus a half mv initial squared. In this case, v final is 10, is 15, v initial is 10. What do you get? You know, I typed this all in. I think I can just backspace and make the 10 a 15 and make the 5 a 10 squared. Have I gone on a rant occasionally about getting a good calculator? I hope I have. And I got 4,512.5 joules. The faster you go, the more work it takes to increase your speed, the more energy it takes to increase your speed. Why? The work-energy theorem, and that's squared. Is that okay, Ron?
Yeah.
Good. Next page over. A model rocket reaches a height of 340 meters when launched. If the top speed of the rocket is 85 meters per second, how much work does the rocket engine do on the rocket? Or how much chemical energy must be stored in that rocket engine? Or if we were doing this on a larger scale, how much rocket fuel does NASA need to put in to get it way up there? Not 85 meters, but way, way, way higher. We'll look at that particular question next year because I have to teach you Newton's universal law of gravity first. Well, Kenley, what's this question want me to find? How much what? And again, my first thought would be, don't write this down, force times distance. Now, this is tricky because I do see a meters. I think I do see a distance. I said, don't write this down. Okay. So I would say to myself, maybe I'm going to do that. Well, that doesn't take into account that they gave me a speed. And I don't see a force. Definitely, I don't see newtons anywhere. I don't even see an MA in disguise. I don't see a mass or an acceleration. You know what? Nuh-uh. It's also the area underneath the force versus distance graph. Okay. Now we'll write down the work-energy theorem. Change in potential plus change in kinetic. Kenley, in this question, is there a change in height? Yeah. Is there a change in speed? Yeah. Now, previously when I've said those two words together, I've also said, is there a yucky curvy path? Is the job for conservation of energy? I'm not saying that because I already answered the question. What are they asking me to find? Work. So this is not conservation of energy. Gee, there's work. Okay. It's going to be mgh final minus mgh initial plus a half mv final squared minus a half mv initial squared. You know what I should have said, Kenley? What's changing anything? You wrote it down on the previous page somewhere, I hope. It's also on your green sheet, top right corner of your green sheet. Delta equals change in equals, loud and proud, what? So change in potential, final minus initial, change in kinetic, final minus initial. Hey, are any of these zero? I didn't hear you. I think you're right, but I... Oh, this one? Starting at rest? And you know what? I think I can do that because I'm pretty sure we're starting on the ground. Okay. This is how much chemical energy needs to be stored in this rocket engine. Now, this isn't quite right because, Carlos, we're ignoring air resistance. As I've told you, air resistance is a bear to calculate. In real life, NASA going into orbit would have to take in a lot of air resistance. We're not going to worry about that. So it's going to be M.15, G 9.8, H 340 plus 0.5, 0.15, 85 squared. How much energy has to be contained in this rocket engine if I want it to do this? Do you all get 1041.675? I'll go 1000. You know what? I'll go to 3 sig figs. 1040. 1042 to 4 sig figs. 1040? Yes? No? See nods? Okay. Number 3. I like number 3. I like number 3. I like number 3. Number 3 is a nice question. Savannah, what's A want me to find? Keep reading. I think that phrase is important because I think they just told me V final. What's V final going to be? Okay. Work is force times distance. Do you see a force? Do you see a distance? It's also the area underneath the force versus distance graph. Do you see a graph? This is work-energy theorem. It's going to be work equals the change in potential plus the change in kinetic. And again, I'm lifting that right from the green sheet. Make sure you know where that is on the green sheet. Savannah, reading this question, does it hint that there's any kind of a change in height or anything like that? Now, if I gave this to you on a test, and I might, I would probably say is traveling on a level road at. I would make sure that you didn't have to guess. But here, I think it's reasonable for us to say, I don't think there's any change in potential energy because it didn't go up or down. What's changing anything? It's on your green sheet, top right corner. Okay, so the change in kinetic is going to be KE final minus KE initial. This one's a little strange. The final kinetic is 0 because you told me it comes to a stop. Yes? So I'm going to get this. Work ends up being negative a half mv initial squared. It ends up being negative 0.5, 1250, 35 squared. Negative 0.5 times 1250 times 35 squared. What'd you get? I got a fairly big number, which actually makes sense because 35 meters per second is about 100 and some kilometers per hour. You know what? I have a feeling it would take a lot of work to stop a car that was traveling at freeway speed. I'm okay with that. It's not something a human being could do casually. I'm going to write down the whole answer. Negative 76562, negative 765,625 joules. Why negative? Because the car has to lose energy. This is saying how much energy does the car need to lose? You need to lose 765,625, or if instead of saying the word lose, put a negative in front of it. Okay, cool. Antonio, what's B want me to find? What else did they give me in B? What did I find in part A? So here's what I just heard you say. They want me to find force. They gave me a distance. I already know work. It would be convenient if there was an equation that had force and work and distance in the same equation. Is there? What? Can you get the F by itself, please? Which work? Negative 6765625. Which distance? 82. Now, I'm going to get a negative force. What that's saying is the force has to be in the opposite direction of motion, because force is a vector. If the car is going forwards, the force has to be backwards. If the car is going north, the force has to be south. Which, yeah, okay. I'm going to go negative 9340. And force units, Antonio? Good. Logan, what's C want me to find?
The minimum coefficient of friction.
Yeah. What was our symbol for the coefficient of friction, Logan? Do you remember? Hey, what's mu? I don't know. What's mu with you? This is asking me to find mu. Logan, what did I find in part B?
The force.
Yeah, which force did I find in part B? If I gave that force a name, I would say the force that brought the car to a stop is the force of what? What?
friction.
Yeah, if you want to, you can go back in part B and you can actually put a little. What we found was the force of friction. Logan, what's part C asking me to find?
Minimum coefficient.
It'd be cool if there was an equation that had the force of friction and mu in it. There is one. And it's good review. You've heard me say many times, friction is what times what. And many of you have said back, I can see Courtney's lips moving. You're right. Mu times the normal force. Can you get the mu by itself, please? Am I correct in it's going to be friction divided by the normal force? Is that right? Yes? Now, I should say this is a job for a free body diagram, but let's see if we can just imagine it. Because the force of friction is negative 765. No. The force of friction is 9340, but I'm going to use my answer button. I chucked the negative this time because mu is never negative, it's positive, over the normal force. I don't know the normal force. Can you imagine the free body diagram? I think this is one where I would say, oh, but look, another force the same size as the normal force. I think it is going to be over mg. Now I wrote 9340. You know I'm going to use my answer button. So it's going to be this. I'm going to ignore the negative. If I want to get rid of the negative, I could just divide by -1 or something like that. That would get rid of the negative. So it's going to be this divided by, I've scrolled down. What was the mass? 1250 times 9.8. I know that road tires have a mu of around 0.5, 0.6, 0.7-ish. Let's see if Mr. Dueck made up good numbers, because I do like my numbers to be accurate. Sure, these are pretty good road tires, 0.76, 0.762. Who remembers, what were the units for mu? Was it a force? Not a force, so no, what? It's newtons divided by newtons. The newtons would cancel. It's a unitless measurement. Doesn't have any dimensions to it. Turn the page. I'm fulfilling a promise from November. Way back in November, we did an RCMP question where I had the RCMP had some skid marks, and then I had to add this stupid coincidence. I said the driver was on their cell phone and the voicemail to their neighbor picked up the sound of the skids, so we know how long they were skidding for. We know time. Of course, that's never going to happen in real life. And I think I said to you back then, right now we don't have the physics to do this the way the RCMP would. But ladies and gentlemen, now we finally do. Read along with me. It says this. An RCMP officer is investigating an accident. A car struck a pedestrian at a school crosswalk. No witnesses. But the RCMP uses a device to measure how sticky the pavement is right there. It has a mu of 0.65. And with a tape measure, she measures the skid marks, 49 meters long. Should the RCMP press charges? We can now actually decide. We can figure out. By the way, what do we want to find? Can anybody see out of this what we really want to find? If I'm going to press charges. Adam, I can't hear you. VF is 0, I think. VI. VF in any car accident is always 0. VI. Okay? You with me on the argument there? How are we going to put all this together? This has been a year culmination of physics to get to here, because I always try and show you where this is used. This is going to sound really, really strange, but I'd like you to write work equals work. Well, duh. No, humor me. Write that down, please. And what we're going to do, Kenley, is we're going to combine two definitions. We're going to go force times distance equals change in potential plus change in kinetic. With me so far? Work equals work. This left-hand side, I have enough information to solve for. So I'm going to turn this into a number. The distance is the skid length. Did they tell me that? Yeah. Which force, what force is it that brings a car to a stop? So let's add a little there. You can drop your equal sign down, and then if you want to, you can just put little ditto marks on the right-hand side. That's going to just keep dropping down for a while, but I don't feel like rewriting it. Have you seen that little trick where you put quotation marks, and that just means the line dropped down? Okay. On the left side, friction is what times what? Mu times the normal force times distance. I don't know the normal force. Oh, but look, another force the same size as the normal force. Can you imagine the free body diagram? So we have this. mg down, normal force up, and friction, if the car is slowing down, would be pointing backwards. I don't have to have a force pointing forwards because I want the car to be slowing down. That will slow the car down. I don't know the normal force. Oh, but look. Which one? So I can say on the next line, ditto mark plus ditto mark, mu mg d. Hey, Rowan, what's mu? I don't know. What's mu with you? No, from the question, what's mu? Yeah, so the RCMP, they have a device where they can measure how sticky the pavement is. That you would, if you were the investigator, you would collect that from the scene. You'd probably try and do it in the same weather conditions. So you would, oh, if it's raining, I'll do it when it's raining. Try and do it at the same time of day, but you could get that. What's D? What's G? What's the mass? I wonder if it will cancel. Maybe there will have an M in everything. Maybe I don't actually need the mass of the car, because that would sure be handy, especially if it was a hit and run and I don't know what the car is. Let's find out. So the left-hand side, I've got to mu mgd. On the right-hand side, you know what? Because I don't see a hill here. By the way, if there was a hill here, I could factor it in. It would just add a level of complexity. Okay. What's changing anything? So I'm going to get, have I got lots of room? Good. I'm going to get this. Mu mgd equals 0 plus a half mv initial squared. Sorry, not plus. You said final minus initial. No, minus. Why is the final 0? Oh, Adam, what's the final speed of any car accident ever? So your final kinetic energy was there. This is what you started with. Where'd that energy go, by the way? The heat that created the rubber, that heated up the rubber to create the skid. That's where most of it went. Probably would have been some noise as well. Okay. Really what I get then is that. Like 0 minus anything is just minus the thing. You okay with that argument, Rowan? How many terms are there in this equation, Rowan? Is there an m on the left-hand side term? Is there an m on the right-hand side term? So even if this was a hit and run and I don't know what the car is, could I still figure out theoretically how fast they were traveling? Well, that's handy. What was I trying to figure out? Sorry? Which is what in this equation here? Okay, now I'm going to do one more thing. I'm going to drop the negative. This negative here is telling me we're losing energy to slow down. Technically, I should have made this force negative because it's in the opposite direction of travel. I'm just going to say on my next line, everything is backwards in the same direction. Let's just all call that positive, and it makes the math much nicer. Okay? Get the V by itself. I could either divide by 0.5. If it's okay with you, I'm going to times by 2 instead, because it's going to look prettier. And I'll get this, 2 mu g d, that equals vi squared. What? Sam? I heard you whisper it. I thought I heard you whisper what to do next. Yeah. Isn't that what you whispered? No?
No.
I thought someone right there said that. Sorry. Here we go. And this time I didn't need that coincidence of the cell phone picking up the... In fact, I didn't even need the car. Then I go look for someone who's got unexplained damage at a body shop. Try and match some fibers or some DNA or whatever. So it's going to be the square root of 2. Was mu 0.65? G is 9.8. And the distance, what was the distance? 80 what? Sorry? 49. Not 89. 49. Now this is the minimum speed because they could have slowed down before they started skidding. They might have been going faster, but they had to be going at least this fast. What'd you get in meters per second? Sorry? So 25? Anybody else? 25. Could you multiply that by 3.6 to see how many kilometers per hour? And this was in a school zone. So this would probably be enough to charge them with some type of vehicular manslaughter. Like you could charge them with something fairly serious here, as opposed to just, here's your fine, don't be stupid. You could take this to court. So I promised you back in November that we would revisit this RCMP question. This is how you could do it. Now, if you really wanted to bring this to a court of law, you'd probably need to take air resistance into account a little bit. Although I gotta be honest, for a vehicle slowing down, air resistance doesn't play that big a role. I think you'd be okay. Is this the last one? No. I'm gonna do the motorcycle video later. I might have to skip it. We're gonna instead get to example 4. I like example 4, I like example 4, I like example 4. Example 4 is a nice question. It says, a car is a rocket car, is initially at rest on a, I should probably mentally or physically underline that, on a frictionless horizontal surface. Okay, horizontal, so no change in height. The engine is ignited and the graph below shows the thrust force versus distance traveled. So here's the graph. First question, why do you think the force decreases after 15 meters? I notice the force is 160 newtons and then all of a sudden it starts getting smaller. Why do you think it's happening? Any of you seen a rocket engine? Yeah. Running out of fuel, yeah. So why do I think it's decreasing? Now, I have to be honest, Blake. In real life, I think it would probably look like a curve, but you can't find the area underneath the curve, so I fudge the numbers and I'm keeping everything nice lines because that's the math skills that you have right now. So full disclosure, we're doing some sloppy physics here, but we'll be close. We'll be close. Jackson, what's B want me to find? How the heck can I do that? I haven't given you much information at all. Ready? Work equals work. Well, duh. No, write that. Change in potential plus change in kinetic Can you read me that word, Jackson? Don't think there's any change in potential. No hill. What's change in anything? It's on your green sheet, top right corner. By the way, I don't mind if you don't have it memorized. What I do mind is if you freeze and go, how will I figure that out? Then it's probably on your green sheet, right? Okay, so make sure you know where it is. What was that? So this is going to end up being a half mv final squared minus a half mv initial squared. Wait a minute, what was v initial? If I can find something on the right-hand side, Jackson, then I'm just getting the v by itself. What's on the right? Sorry, on the left-hand side. I said right, on the left-hand side. What's on the left-hand side? Work. Now, I can't go, don't write this down, don't write this down, do not write this down, but look up. Why can't I go force times distance? Because the force here is not constant. See how it's getting smaller? What was my second definition of work? Oh, it was an area. That area. So if you want to, you can write the word area right there. And then over here in the margin, we're going to calculate the area. What two shapes is this area made up of, Jackson? So I'm going to go like this. I'll put a big 1 there and a big 2 there. And I'm going to find area 1, rectangle. That's going to be length times width, or base times height. Its area is going to be what times what? Wait a minute. Pause. After how many meters? Ha! We just want area 1. How fast is it going after 15 meters? Cool. What's this area? It's going to be, I think, 15 times 160. Length times width. Is that okay? So that number is going to go right there. What is 15 times 160? 2,400? How will I get the V by itself? Divide by M, and either divide by 0.5 or times by 2, and then, Sam? Yeah, thank you. I could hear the little hamster on the wheel. Squeak, 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 squeak. Ah, it's square. So if I hear you correctly, you're telling me V final after 15 meters is going to be 2 times 2,400 divided by the mass square root. I gave you the mass. I hope, did I not? Up there somewhere? I did? So it's going to, what was it? 5. So it's going to be, turn that on, 2 times 2,400 divided by 5.2 square root. This isn't going to work out evenly. 30.4. It's a rocket car. It should be going pretty quick. Is that okay, Jackson? Cool. Jagger, what C want me to find? I'm going to do exactly the same thing, except after 25 meters, it's going to be the whole area. The rectangle plus the triangle. So I'm going to again say, hey, Captain Obvious. I'm going to again say area equals a half mv final squared. V initial, 0. So the area from shape 1, we already said was 2,400. The area from shape 2, Jagger, what shape is shape number 2? Who remembers what the area of a triangle is now? If you don't know the area of a triangle or a rectangle, you might want to add that to your green sheet, but I'm also going to say maybe you kind of want to maybe have it memorized. Yeah. I always think of it as base times height divided by 2, but yeah. It's half a rectangle. So the base is that long right there, 10. The height is 160 divided by 2. 10 times 160 divided by 2. 800? No? Am I wrong? Courtney, question? Right? 10 by 160 and divided by 2. Is it 800? Oh, okay. Nobody said anything. Now that's the triangle, but the total area is going to be then 2,400 plus 800. That equals a half mv final squared. And Sam, now we're back in familiar territory. Divide by m times by 2. Yeah. Oh, thank you. So V final is going to be 2 times 3,200 divided by 5.2 square root. What'd you get? $35.1? Now, I want you to think about what we were just able to accomplish, Jackson, by giving me the graph and the mass. That's it. I was able to figure out a lot of pretty good information. The work-energy theorem, really nice because it unites work, force, distance, and energy potential and kinetic. Okay. There's almost certainly going to be a question on your test where I give you a graph, a force versus distance graph, and I ask you to figure out how fast something is going from that graph. It'll be the area equaling the change in potential plus the change in kinetic. What's your homework? I like number 1. I like number 2. You know what? I'm going to skip number 2 and do number 3 because number 3 actually wants you to then find the power. 4 is good. Five is good. 6 is good. I'm going to pass on 8. It's cool, but that's okay. I'll do 9. I'm going to pass on number 10. And I have for you a take-home quiz as